the red pill of machine learning. Welcome, Monica. It's great to have you here.
Thank you.
Monica Anderson is an independent AI and ML researcher and the founder of Syntience Inc.
Correct.
Her work is focused on epistemology of AI, but all her theory is based on her experiences of design and implementation of understanding machines based on deep discrete neuron networks since January the 1st, 2001. And you used to work for Google as well, I might slide in. So welcome and thanks for joining us. And I'll hand the floor over to you, Monica.
So my goal with this talk is to sort out the reasons for the cognitive dissonances experienced by machine learning practitioners, especially newcomers. Start with a slide to introduce myself. I'm from Sweden. I'm a US citizen. I got a master's in computer science with a double E minor. English is my third language, and I have used 30+ programming languages professionally. I'm in a very small group of people that have been researching deep neural networks full-time since 2001. Most people only got to it 12 years later, 11 years later in 2012. I'm an ex-Googler. I founded 3 California C corporations, and Syntience is my research company founded in 2004. Let's start with a motivating example. What is machine learning really like? Beginning machine learning students are given exercises like this one. A given large spreadsheet lists data about houses sold a certain year in the US, which includes, among other information, the zip code of the house, the living area in square feet, lot size, number of bedrooms, number of bathrooms, the year the house was built, and the final sale price of the house. We would like to be able to predict this final sale price given the corresponding data for the current house that we are about to list for sale. The given spreadsheet is the data the student will use to train a deep neural network. It is the entire learning corpus that we need. So students can download deep neural network libraries like Keras and TensorFlow and runnable examples for many kinds of problems from places like GitHub and glue/superglue. The code may require some customization to adapt the file formats, etc. Next, the student trains the network using the given data. This may take a while, but when it finishes, they can give the system data for a house that didn't exist in the training set, and the network will quite reliably predict what the house might sell for. This was the goal of the exercise. The student has created a system that understands how to estimate real estate prices from listings. But when done, the student still doesn't understand anything about real estate. The predictive capability that many people in real estate should be willing to pay money for is 100% based on understanding in the deep neural network, in the computer. This is a rather important point. And because all libraries and many pre-sold examples of this nature are freely available, the student will not have to do much programming at all. This is desirable. This is what AI means to me personally, at least. The computer understands the problem so that we don't have to, and we don't have to do almost any programming either. So deep neural networks, they may seem very strange to you, especially if you are a scientist. The new cognitive capabilities in our machines are the result of a shift in the way we think about problem solving. This shift is the most significant change in artificial intelligence ever, if not in the science as a whole. Machine learning-based systems are now successfully attacking both simple and complex problems using these novel methods. You're experiencing a revolution at the level of epistemology. This will affect much more than just the field of machine learning. We want to add more of these new methods to our standard problem-solving toolkit, but we need to understand the trade-offs. So this talk intends to demonstrate that understanding deep neural networks requires a holistic stance, which is, at important levels, blatantly incompatible with the reductionist stance of modern science. As practitioners of deep neural network technologies, we sometimes adopt strategies that seem to contradict many of our core scientific convictions. We may get the feeling something is wrong. These trade-offs are real and meaningful, and the counterintuitive choices make perfect sense when viewed at the level of epistemology. Improved clarity in these matters should alleviate some of this cognitive dissonance and may accelerate progress in the field. The title of the talk is a Matrix movie reference to the eye-opening clarity some machine learning practitioners might achieve after learning about and adopting a holistic stance. These ideas are important in several problem domains at multiple different levels. We have two very different processes in brains. We have two ways to understand the world, two ways for humans to solve problems, two ways to approach artificial intelligence, and two ways to use computers to deal with human languages. So we're going to mostly work on the third one from the top, two ways for humans to solve problems, but I will introduce my specialty, which is natural language understanding, the fifth point, first in one slide. So NLP is classical natural language processing. It relies on human-made models of some language, such as English, and perhaps models of parts of the world. NLP uses things like grammars, word lists, dictionaries, lists of city names and people names, etc. In contrast, research in NLU, which is natural language understanding, tries to get computers to learn to understand human languages simply by reading books in the target language, any language. The goal is some kind of human style and useful, but not necessarily human level understanding of language. Any world knowledge would be a bonus. We note that classical NLP and modern NLU have chosen opposite answers to many difficult binary choices. In the tables that follow, NLP is left column and NLU is right column. Let's consider humans solving everyday problem now at various levels. There's basically, you can have any problem you have can be solved in either of two different ways. You can plan something in some detail before doing it, or you can just do it. The difference is much larger than one might think. Our brains can handle either strategy, but when it does, it's running different kinds of processes. That's another talk. Programming is an example of planning something in detail. But now, starting with the AI/ML revolution of 2012, we also know nowadays how to teach computers how to just do it, which means no further programming. This has totally changed how we are building systems with cognitive capabilities. Everyone working in machine learning or AI needs to understand the trade-offs we must make at the most fundamental, which is the epistemological levels. The 2012 revolution requires unlearning and seriously rethinking many things we were taught to vigilantly strive for in our STEM educations. Things like correlation bad, causality good, and do not jump to conclusions on scant evidence. But when building understanding systems, correlation discovery and handling of sparse and inconsistent input data are exactly the kinds of tasks we will have to perform and perform well at these pre-scientific levels. Think about walking across the floor. You're sequencing your leg muscles. Well, you're doing it with your brain, but you can't consciously plan the sequencing because you don't even know what leg muscles you have. So walking is a learned skill. As another example, tell me how you understand this sentence. Do you use grammars? Do you even know how your language understanding works? We really don't. These are subconscious skills that we cannot examine using introspection any more than we can say what a specific retina pixel is seeing. You actually do most of the things you do every day without any reasoning whatsoever. These are learned skills. Let's look at some terminology here. At the epistemology level, the math and science approach to solving complicated problems by reasoning is called the reductionist stance. The just do the obvious thing approach to solving complex mundane problems or complicated, complex scientific problems like protein folding by only using understanding of the problem is called the holistic stance. Reductionism and holism are not dirty words. They are established terms of the art in epistemology. Reductionism as a methodology is often blamed for bad and biased science. Yes, sometimes reductionist science is bad. We just need to get even better at the science. Reductionism is the greatest invention our species has ever made. Let me say that again. Reductionism is the greatest invention our species has ever made. And holism is not really about crystals and aromatherapy. Many people prefer one or the other if they can choose, but most of the time there is no choice. As practitioners, we need to know which tools to use in any project, and we need to know this at the planning stage. So let's define and discuss these terms. There are many different but compatible definitions for reductionism. In this talk, I will use my own definition for reasons of simplicity and clarity. Reductionism is the use of models, which are scientific models, theories, hypotheses, equations, formulas, naive models, which we don't communicate to others, superstitions, which are theories which are wrong, and most computer programs. Models are simplifications of reality. A model airplane has no instrument panel. We can design new models using observations, experiments, math, and reasoning. Models ostensibly require a scientist to create the model. We can use a PhD degree as a license to create models. Models ostensibly require an engineer to select the model and use it to solve a real-world problem. Both creation and use of models requires that you first understand the problem and the problem domain. This is very important. In the reductionist solution, a human has to understand the problem and the problem domain and come up with a model using a process we will talk about later called epistemic reduction. In contrast, holism is the avoidance of models. Holistic agents solve problems directly in the problem domain using understanding, not models. People and holistic systems can discover new solutions by trial and error or other holistic methods, also known as model-free methods, and then remember what worked and what didn't. When faced with new problems, a holistic system performs pattern match operations to prior problems, hoping to be able to reuse previously discovered working solutions. Well-working solutions are remembered. Holistic agents all learn from their mistakes. This is one of the most certain signs that you're dealing with a holistic system, because in reductionist systems, they are designed and implemented by humans, and improvements require a new version to be created and released, for instance, after a programmer has learned from their mistakes. So that's a very important point. We'll get back to that. Let's compare science and epistemology briefly. We know what scientific models look like, equations, for instance. But what do epistemological equations, so to speak, look like? They can't be expressed as scientific equations because they are pre-scientific or non-scientific. Consider this statement: you can only learn that which you already almost know. This is a quote from Patrick Winston at MIT. This is why we don't teach calculus to 1-year-olds. To detect novelty, you need to remember everything old. I figured this one out, not too hard. You are known by the company you keep. This is the naive holistic version of the Yoneda lemma, which justifies the use of embeddings in language understanding. Science has no equations for concepts like understanding, reasoning, learning, abstraction, and modeling. And to me, as an implementer, is very important. Epistemological truth can be used as AI implementation hints, but science provides very few such hints. I specifically am avoiding neuroscience. So let's look at difference at the level of epistemology here. This is the first real table we're looking at. We have discussed most of these already. So the first three are explained in more detail in my artificial-understanding blog. So we have the use of models and avoidance of them. We have reasoning versus understanding. We have reduction systems require understanding, and holistic systems can provide it. Solved in the model space versus directly in the problem domain. And the reductionist solution is optimal in many domains. And I have to emphasize this again. If you have a reductionist solution for a problem that works well, by all means, continue using it forever. There's no point in bringing in an AI at that point. You use holistic methods only when reductionist methods cannot be used, such as when you're dealing with complex systems where everything affects everything else. Consider cellular biology, the stock market, the global economy, etc. These are all the brain, the drug interactions in the body. These are all systems where everything affects everything else, and reductionist systems are really poor at dealing with that. And this is where machine learning and holistic methods really shine. So let's look at some main trade-offs here between these two systems. In the reductionist case, we have optimality, which is the best answer, completeness, which is all answers, repeatability, the same answer every time, extrapolation in low dimensionality problem spaces, parsimony, which means don't waste resources and favor succinct explanations, transparency, which means we can understand the process to get the answer, explainability means that we understand the answer. These are great things. This is stuff reductionists love. And it would be really hard to give up on all of them, but that's what we have to do if we want to switch to a holistic stance. In the holistic end, they are rough comparisons, rough equals to each other here, but don't take that too seriously. In the holistic case, instead of optimality, we get economy, and we reuse known useful answers. We get promptness, which means we accept the first found useful answer rather than trying to find all of them. We get improvement. I mean, instead of repeatability, if we learn from our mistakes, the system gets better over time. And if you want repeatability, you can have it. If you want improvement, you can have it. But you can have the repeatability even in the holistic end with a little bit of trickery. Interpolation. This was where extrapolation could only work in low dimensional domains because they had to work in the model space. When you're working directly in a gigantic space with millions of dimensions, for instance, you can do interpolation in those spaces, even in super high dimensional problem domains, because the interpolation is at this point is more reliable. You can use it over very large sets of data. We can use parallelism, which we do when we don't know exactly how to solve a problem. We can pursue multiple paths in parallel, and this is much more expensive than the parsimony of the reductionist side. But sometimes that's the only way. We do basically exhaustive searches if we have to. Intuition means that we accept useful answers even if they're achieved by unknown or subconscious means. And ignorance means that there's no need for humans to model or even understand the problem or problem domain. And this is the most controversial statement, I think, in the entire talk. So let's look at it a little bit closer. Ignorance is a feature. Explainability in the reductionist end means basically understand the solution. But ignorance in the holistic side says no need to even understand the problem. No need to even understand the problem. Like we said, in the original example, we had this student who didn't understand anything about real estate. Our machines understand our problem for us. Early AI will manifest as machines that can solve problems we ourselves cannot understand or cannot be bothered to understand. It turns out to be very common that instead of trying to analyze some problem with the domain, we just say, learn it and be done with it. And surprise, we're already at this state. We already have what I think of as AI, as programs that can solve problems that we can't solve ourselves, because we have, for instance, protein folding and Go and so on. So we are delegating our understanding to our machines because we want to be increasingly ignorant about increasing amounts of stuff that we don't care about. We are pursuing AGI so that we may play, as Philip is fond of saying. So let's look at some advantages of these holistic methods, such as neural networks. NP hardness. It is because we desire certainty, optimality, completeness, etc. that NP hardness becomes a problem. There are many problems where it is relatively easy to find a provably valid solution, but where finding all solutions or the optimal solution can be very expensive. Real-world traveling salesmen merrily travel along reasonable routes. In holistic systems, GIGO, which stands for garbage in, garbage out, is not a problem. It is a requirement of real-world intelligence systems that they be able to detect what is salient and likely to be correct in their input streams in order to avoid attempting to learn from noise. They need to be able to detect omissions, duplications, errors, noise, lies, etc. And the only way is to relate the input to similar input they have understood in the past. What they already know, in other words. An example of the utility of this is the current crop of image and video apps featuring image understanding based on deep learning. These apps can remove backgrounds, restore damaged photographs, etc. We need to keep in mind that the ability of holistic systems to fill in data and detect noise depends on them having learned from similar data in the past. Here is an example. Garbage in, garbage out is not a problem. This should not be a surprise to you if you have correct expectations about artificial intelligence. Brittleness. Most of cognition is the recognition. Being able to recognize that something has occurred before and knowing what might happen next has enormous survival value for any animal species. A mature human has used their eyes and other senses for decades. This represents an enormous learning corpus, and they can understand anything they have a prior experience of. As they get closer to the edge of their competence, the quality and precision of their guesses will start to decline. The mistakes made by humans, animals, and by holistic machine learning systems are very often of the near miss variety, which provides an opportunity to learn to do it better next time. Contrast this to the reductionist software systems created for similar goals. Rule-based systems have long been infamous for their brittleness. As long as the rules that match the current reality perfectly, the results will be repeatable and reliable. But in corner cases, when the matches become more tenuous, the quality rapidly drops, and simple internal mistakes will lead to such systems to return spectacularly incorrect results. Let's consider obsolescence. As I said, sometimes repeatability is important, and sometimes tracking a changing world by learning more about it is important. Human-made models tend to have more abrupt edges to their competence and few ways to make partial mistakes. In machine learning, continuous incremental learning makes it possible to stay up to date. If we want repeatability, we can emit the condensed and clean and frozen competence, so to speak, from a learner that can be loaded into a non-learning, read-only, cloud-based understanding machines that serve the world and provide repeatability between scheduled software and competence releases. A few higher level advantages to holistic systems: intuition, understanding, decent estimates of saliency, epistemic reduction and abstraction, which is abstract, they are discussed in my blog, disambiguation of language, for instance, self-organization and self-repair, scaling very nicely, and creativity cannot be had in very strict reductionist systems. So let's go back and look at the details of the original list of the 5 dichotomies that I had. We had epistemology, which has reductionism and holism. The brain has reasoning versus understanding. The human problem solving uses STEM and other STEM education, other reasoning-based methods versus just do the obvious as the holistic end. Strategies for AI, the reductionist AI was basically a 20th century AI before 2012. And after that, we think of machine learning and deep neural networks as the way to go. And finally, human languages is the split between NLP and NLU that I described earlier. So this is basically the red pill of the talk, cognitive dissonance. Throughout our STEM education, we have been taught how to build and use models. Do not use correlation to imply causation. Do not jump to conclusions on scant evidence. Science has deprecated holism for 400 years. Suddenly, after 2012, deep learning starts solving complex problems holistically. Science itself now has a cognitive dissonance. Okay. It's not all bad news. We can double our toolkit. All humans use holistic methods from birth. And then we learn to walk and talk using holistic methods. A STEM education comes after that. It teaches reductionist problem-solving methods as a discipline. And I'm serious when I say discipline. This is something you have to vigilantly maintain in a disciplined manner, because the temptation to jump to conclusions is always too large, because that's our natural way of solving problems. So the deep learning revolution in 2012, it made these holistic methods available to computers. Okay. And it's a wonderful match, because many of the remaining hard problems that we have in society, such as global economy and other things, they are complex problems. Everything affects everything else. And we need something like AI, or in the beginning, we need something like holistic methods. And later we will segue into AIs using those holistic methods. Natural language understanding is mostly holistic. Language is just another simple, mundane, everyday problem to our brains. If we can learn one thing, we can learn another. Full intelligence, in my opinion, is something that combines a holistic subconscious understanding, subconscious in the case of a human brain, with a reductionist conscious reasoner. And you can remember that you cannot reason about that which you do not understand, which means that holistic methods provide understanding. Reasoning requires understanding, which means that understanding must precede reasoning. And it does this in multiple places. It does it in our brains because it takes about half a second for our brain to understand the visual field and send signals to the reasoning and conscious parts of our brain what's going on. And this half second is masked by the brain itself. It lies to us to make sure we don't notice. You can read all about this in Dennett's Consciousness Explained. And so there, the understanding precedes the reasoning part. We also see that in the evolutionary record, where lower animals, such as dogs, for instance, they can understand a lot, but they don't reason much. And we are basically the only species that reasons in a serious manner. Some birds do too. So general intelligence. Humans are not general intelligences, right? At birth. Humans are general learners, capable of learning anything. AGI implies a human-designed, hardwired, programmed, ready to run from birth artificial intelligence. This is silly. We need AGL. Machine learning is the only path to AI, to true AI, in my opinion. If at first you don't succeed, lower your expectations. If we can't make an intelligent machine, can we make just the understanding part? Jeff Hinton and others developed deep learning in 1984 to 2012. I developed organic learning from 2001 to 2017. So how do you design an understanding machine? Brains jump to conclusions on scant evidence, because scant evidence is all we will ever have. You don't know what goes on behind your back. You don't know what goes on in the next block. If you want to estimate Apple's stock price a week from now, you have no idea what goes on in Apple's customers' heads, in the White House, in Apple's boardroom, or in China. Scant evidence is all we ever have, and everything we do is a guess. Brains guess and get it right most of the time because we rely on our experience for making those guesses. We interpolate over experience. Let's make our machines do the same. DNNs, like deep learning, are designed to learn, to guess, and to jump to conclusions on scant evidence. Deep learning is not very scientific. Neither is my own stuff, just putting it there. I have invented a machine learning algorithm that is about 1 million times faster than deep learning for natural language understanding tasks. There's an asterisk there. It learns a useful amount of any human language in 5 minutes on a laptop without a GPU by just reading untagged text using 100% unsupervised learning. It learns enough to pass my very simple non-adversarial classification tests at 99% correct. So organic learning is a deep discrete neuron network, DDNN. The neurons are discrete. They are not arrays of floating point numbers like they are in deep learning. I have Java objects that simulate neurons and synapses. It's designed to learn any language by just reading text. It can learn from continuous text streams. And deep learning in general, I think, only works with 300 words in a batch, and then it has to, because it has to do all this jazz with the GPUs. And then it takes another 300 words. This can learn in real time at about 2 kilo characters per second, 2,000 Unicode characters per second, indefinitely. It emits a competence to be loaded into UM1, which we'll discuss in the next slide. I will demonstrate a learner after the last slide here. So if you hang around, you'll see a demo. UM1 is Understanding Machine 1. It's a cloud-based REST service. I have had it running since December of 2020. It provides understanding as a service. It's in the same class as GPT-3 and Google BERT, but it is nowhere near as powerful. It's just very fast and cheap. You send in text and you get back UM1's understanding. This understanding may differ from yours, just like yours might differ from that of a coworker, but will still be useful in most apps that need understanding technology. So let's look at the algorithm that the understanding machine uses. I will not show you the learner algorithm because that is proprietary to my company, but the understander we will license to customers and others. And so we can see how that works. This is basically pretty revealing stuff about my algorithm. So we have an input text stream. This happens to be from Jane Austen. And we have a letter that's being read, a Unicode character. And we look that up in a hash map in our Java program, and we basically find a reference to a node. There is one input node per character in the Unicode alphabet. And when we read that character, we tickle that node, and the node will signal its target links like axonal tree in brains. And they will in turn tickle their target links under certain conditions, and only some nodes propagate it depending on many things. Every node has an ID number. We start out empty. The system starts out absolutely empty, and we create nodes as we need them. We find a new character we've never seen before, we create a node to hook up to that. And when we want to signal somewhere, we might want to make more nodes. So every node is sequentially numbered from 1. And what we do is we know that some nodes are known to be more salient than others. They're more important nodes because we think that our algorithm thinks that they embody important higher level concepts. And so then the ID numbers of those nodes are returned to the API caller. This array of numbers is basically the UM1 understanding. To recapitulate, we use a numbered neuron API. We send in some text, get back a list of numbers representing salient concepts found in the supplied text. Each number is the ID of an activated discrete pseudoneuron. Their meaning is opaque to the caller, but that turns out not to be a problem. This is described in the API manual. It's another talk. So, some closing words. Science was created to stop people from overrating correlations and jumping to erroneous conclusions on scant evidence, and then sharing those conclusions with others, leading to compounded mistakes and much wasted effort. Consequently, promoting the holistic stance has long been a career-ending move in academia, and especially in computer science. But now we suddenly have machine learning that performs cognitive tasks at useful levels using exactly a holistic stance. Ignorance of these stances leads people to develop significant cognitive dissonances, which is why discussions about these issues are very unpopular among reductionists. But the dichotomy is real, we need to deal with it. The reductionist stance also makes it difficult to imagine accept useful things like systems capable of autonomous epistemic reduction, which means they can discover abstractions on their own. Systems that do not have a goal function, systems that improve with practice, systems that exploit emergent effects, systems that by themselves make decisions about what matters most, and systems that occasionally give a wrong answer but are nevertheless very useful. So we are now finding that after full college education in machine learning, we don't actually need to do almost any programming at all. We don't need to understand anybody else's problem domains, because we don't have to perform any epistemic reduction ourselves. And so data science work is reduced to massaging spreadsheets of gathered data. We should recognize this for what it is. AI was supposed to solve our problems for us so we would not have to learn or understand any new problem domains, to not have to think. And that's what we have today in machine learning and with holistic methods in general. Why are some people surprised or unhappy about this? This is what I think of as AI. This is what we have been trying to accomplish for decades. With expected reasonable improvements in understanding capabilities in our machines, and the acceptance of the holistic stance will become a requirement for machine learning and AI-based work, but it will likely take a decade for our educational system to adjust. Now let's do, before the Q&A, I would like to just do the demo. Let's see if I can do this in some easy way here. I may have to get up. So, can everybody see a blue screen here in the screen share? No,
no. I think you need to change the shared screen within
all right,
Zoom.
Hang on. Yeah. Okay, well, let me find the right windows for this.
I can see the console for directory listening.
Right.
Can't you make the computer just do it?
Oh, you can see a console?
I can see a console for directory listening, but the text is too small for me to see.
I can see it on my 4K monitor. Are you sure you don't just need to do Alt-Shift Meta Option Escape to run the whole demo?
What are you talking about?
Emacs, bad joke.
Oh, I know Emacs. I use all the time. Anyways, let me do this. Can you see? Can anybody see? Can you see anybody see white text on a blue background in my shared screen? Okay, fine. I have lost my main screen for.
Yes. So
there you go. No, you're back.
Okay, so maybe you need to share a different screen from within the
All
Zoom,
right.
from within the Zoom, from within the Zoom interface. So when you click on share screen, you can choose which screen to highlight.
Ah, okay. Hang on. Stop share. I couldn't find a toolbar for this because it was covered as usual. All right, here's the Zoom, and where is my screen share? There it is. And now we try to share. Maybe I have to share this one.
You know, in the 90s, it was traditional at conferences for people to fiddle with cables. And
yeah, that's true. Cables.
Okay, can you see a screen now? Anybody see a screen share now?
Yes.
Yeah, I can see it.
Now we see a blue screen.
Yeah.
So it is blue with white text on it?
Correct, yeah. Cat sample TSV.
Correct. What we're looking at here is the test cases I will be running. This is 2 test cases. They are basically, there is the one that starts with the number 4 and the one that starts with number 0. You have a target sentence, which is, in the first case, is there a reason why we should travel alone? And then there are 5 sentences to choose from. And the task for the computer is to pick the one that has the closest meaning to the target sentence. So this is a multiple choice classification test in a non-adversarial test batch. So it is easy to get to 100% here, and we expect to get there. But this is basically the kinds of class or questions that the test case is trying to solve. And this is roughly the level you need in the chatbot, and this is roughly the level you would need in a email classifier, for instance. So now let's go here and do a Control L and type demo. And we will see here, I hope I don't oversize it, because this would be embarrassing if it folds. Yeah, it folds. Hang on a second, let me minimize just a bit. Ugh. So what we're seeing here is basically a system running, and it is, hang on a second.
I can't see the screen anymore.
Yeah, my apologies. Hang on, Rob. Let me check. Now you should see it. Okay, so what goes on here is that you're running this test, and you can see the columns. I hope you can see the columns. They say test runtime, learned characters, learned seconds, learned. So we are doing here, the important column is the error percent, which is in yellow, the rightmost error column. That basically says how many errors we make. And with 200 test cases, 5% error means that you miss 10 questions. And it has currently learned 200,000 characters, and it is 95% correct. And that took 33 seconds.
Mm-hmm.
Let's have it run a little bit. So it's now at 400,000 characters, reading at 5 kilo characters per second. Spoiler alert, roughly a third of the time it will get to 100% correct. We will not go beyond 2 megabytes, because at 2 megabytes, we pretty much know what it does. Anyways, so this is machine learning of English from scratch, from absolute scratch. Untagged corpus, plain text. We are actually reading Robert Heinlein here for the first 6 megabytes. Any questions about this while we're running it?
What's the events thing in the right column?
If I do something special like what we call a loser collector, the loser collector output, a notification of the loser collector event will happen at the right. Now we're at 98% correct after 800,000 characters. That's basically one Heinlein book.
Would you be able to do it on a maths textbook?
Excuse me?
Would you be able to do it on a maths textbook? This is language understanding.
Yeah. And we don't know. I mean, to be honest, the things that you learn at this level are very, very low level stuff. And if you give the math textbook, yes, it would learn a lot of character sequence useful for math, etc. I don't think it would get a higher level understanding of it, at least not in my implementation here. What we're looking at is basically, this code is running on my laptop, on my Mac. And I have done all my development of this system over the past 21 years on a Macintosh 2013 ICANN cylindrical Macintosh. And I need something like a 3 terabyte RAM machine with 200 plus cores, and those exist and they cost 80,000. So if I give me one of those, I will put in a math book. We're at 98.5% correct after 1 megabyte of learning. So basically, the tests that I use so often, we basically turn off the learning in the learner and use it just as an understander. So it cannot learn from the test, so we can run the test as often as we want, and it takes less than a second to do 1,200 strings for 200 test cases with 6 each. We have a lull here. It went to 1.2 megabytes and it didn't improve. It's just staying the same. Sometimes you get the regressions, but basically this is what we are looking at. We can let it run a little bit longer. Any other questions?
What is the O created and O deleted columns?
Those are, I'm not going to discuss those. They are experimental things that are currently turned off. The current display, incidentally, is over twice as long. This is over a year-old demo. I had this demo made in December 2020. And it matches the cloud-based understander that can do exactly the same thing except in the cloud, and it does it in a couple of seconds for all 1200 strings. Okay, we are 99.5% correct after 1.4 megabyte. So compare this to deep learning. How long would it take to create something like Google BERT? Now, Google BERT is, they ran 100 TPU equipped machines in their cloud for a month. Okay, so they get into the millions of nodes and stuff. I don't show you how many nodes I have in this display. The latest display has a node count, and we typically get into the tens to hundreds of millions of nodes. And I can fit about 26 million nodes in a Raspberry Pi for some decent level of understanding, because the runtime is very small. The learner requires a lot of memory, but the runtime is very small. And it's read-only. So I can have one machine in the cloud with a language model and thousands of processes that are using the same language model in a read-only version. It's going to be very efficient. Can everybody see a annotated version of the run in the share screen?
Yes, we see that.
So forget it. Anyway, you can see here the annotations to this thing, and this version of the run, it reached 100% correct in 3.5 minutes after reading 2 megabytes of corpus. So this is way below what is required. I mean, this is a million times or so faster and cheaper from an energy point of view than what deep learning is for the big language models that they are doing. Okay. So that concludes my presentation. Are there any questions?
Yeah, Monica, can you go into more detail on what exactly is the question, and how do you, what metrics you have for correctness, and that wasn't clear to me at all.
Right. Sorry, that is actually a very common effect of watching those questions, because what we are basically just looking at sentences. They are not questions per se, they are sentences. And they are Quora question pair. They come from the Quora question pair dataset, which is one of the GLUE datasets. And what we are doing is I'm basically using just the pairs of similar sounding questions. I'm not answering them. I say, is this question the same as that one? So it's just a docsim. It's a docsim comparison. It's not a question answering machine. So it is much simpler than you might think. Doesn't answer questions, it just classifies text.
So how does the performance on that task compare with things like Google BERT? Like
it is,
yeah.
Well, it's a different application. I mean, this is only for classification at the moment. I have language generation in the works.
But currently you can use Google BERT for creating just embeddings of sentences and just like semantic similarity search, right? So you can like compare them on the same task.
Yes. Yeah, I have not compared them. I mean, my stuff is very simple, very fast, and very cheap to use. And Google BERT is large, expensive, and I don't even know what the API looks like. The API for this, like I discussed, is basically you get these numbers. I think of my system as a half transformer. It takes text, and in the transformer you have the decoder and the encoder and the decoder. And what I do is I only use the encoder part, and then I take the internal representation and directly use that for the classification.
I have 2 questions for you, if you don't mind.
Absolutely.
So first of all, I think I really like the presentation. The things you went over, right? Like the theoretical foundations between science and epistemology, that's like right up my alley as well.
Thank you.
And also, actually, what you're working on sounds really interesting, related to what I'm working on as well. So I think we should be in touch if we have some room for collaboration, because that difference between understanding and reasoning is something I thought about as well. Now, what I want to hear you elaborate on a little bit is you said ignorance as a feature.
Right.
What are your thoughts on trust and AI safety, and how does that tie in for you with ignorance as a feature?
Well, we're going to talk about it in a few minutes. I understand in the panel, but I can say as much as at this level, everything is very obvious. Everything is the machine has no goal function. It's basically the only goal function you can think of is says learn more, it's so basically in the system that it's not changeable. So trust isn't really an issue. It just does exactly it learns whatever we give it. And this is kind of interesting from a futures point of view, because AI, like I explained in the talk, is going away. It's not going to be programming anymore. It's going to be corpus curation. And that means that us techies aren't the right people to do this. What we have to do is we have to delegate the corpus creation to the humanists, to teachers, to explainers of various kinds, to authors, etc. Somebody has to write the book Gravity for Dummies, because it doesn't exist. And if you're going to learn machines based on incoming text, which is what my belief is, that's how we get first to AI, is basically we create machines that can learn from text, and we give them enough to read so that they understand a large chunk of the world, and it will take a large machine, but it doesn't take any GPUs.
Makes sense. Makes sense. Yeah, I have a similar view on that as well, to where, you know, the understanding is facilitated through what's out there in people's brains and all of that. And then I have a little bit of a challenging question for you. Thanks for elaborating on a previous one, but your comparison between holism and models. Let me ask you this: isn't holism also a particular kind of model?
No, it's the in my talks, it is the absence of models. The important thing is that the main task of creating the model is shifted from the human programmer, if you will, or scientist, to a machine that basically examines the world in many instances by reading a corpus, and it devises, it invents something that we might want to call a model, which I actually really hard refuse to call a model. Let me explain. There's multiple levels in these stacks. I mean, I think of the text as coming from the bottom, and then the nodes at the bottom, they basically signal to higher abstraction levels, if you will, or something else like that. I'm not going to get into the details. But where was I going with this? What was the question again?
If you know, holism is not a particular model as well, and I mean,
yes. Oh, okay.
You make a choice here to say, well, it's specifically not by definition, which, I mean, I guess that's fair enough.
So what happens is that the input layers that we look at, the most closest layer to the input senses, so to speak, they are basically recognition layers. They only determine whether we've seen something before. And if we haven't, then it's alarming and it gets pushed up the chain to the top. If it is known before, we basically push up a little thing that we had one of these again, and it's harmless. I have an example of a holistic system. This is a thought experiment of a holistic system where, and I'm going to go into the vision domain, which I'm completely very poor at. But anyways, imagine a camera that wants to do face recognition. And it basically takes the picture. I mean, there's a picture coming in through the viewfinder, and the machine starts thinking about the picture, and somewhere there is a deep learning machine, and it finds basically here is a light green thing next to a dark green thing, and they're vertical. And then another says, here's another one, and here's another one, and on level up there is some neuron that collects these things, and we are seeing a lot of grass-like things here. So maybe there's a lawn here. Basically, the picture we're looking at is a family sitting on the lawn with a picnic. So it decides that there is a lawn, and basically the bottom layer says here's green and dark green and light green. Next layer says here's grass. The next layer says here's a lawn, and it goes all the way up to the top, and at the top there is somebody who sits and says, lawn, I don't care about lawns, I'm a face recognition expert, forget that. So the trick of basically of epistemic reduction is that at every level in the system, and there's levels in deep learning, there's levels in my systems, at every level in the system, you have to discard that which is recognized as irrelevant and discard it, possibly with a small signal going upward to the next level says, hey, we have a lawn here. I know you're not really interested, but it's there. So the main reason, this is why deep learning is deep. The layers discard irrelevant context, and they can only be recognized. They can only be recognized at their own level. The lawn can only be recognized at the lawn level, and the grass can only be recognized at the grass level. So you have to have multiple layers of increasing abstractions, and then you have to be each of those layers have the power to throw away that which is irrelevant because it's already known and harmless.
Thanks for elaborating. Appreciate it.
Thank you.
So your tool, the party of Le Pen in France would benefit from using it, don't you think?
I couldn't quite understand what you said. Could you rephrase that?
Yes, the party of Le Pen in France could benefit from using your tool.
Really? I should cancel it immediately.
My point is that many anthropological constructions, tribalisms, will use your tool or tools like it. And training your tool on Le Pen would be interesting.
Correct. Yeah, you can put anything in it as a corpus. We like Heinlein because it's Heinlein, and we have to read the stuff occasionally. We might as well read stuff we like. Or we could put in the collected thoughts of Chairman Mao or the Bible or the Quran if we wanted to. And in the beginning, it doesn't matter because it's all the same. It's all just characters. And the only thing it finds in the beginning, like what we just saw, is very simple low-level patterns. And so there is really nothing that even reminds you of ethics at that point.
Can I interrupt? You mentioned the word Le Pen, and that suddenly flashed. Is there a result yet? Are the elections in France known yet? I know it's completely irrelevant, but, well.
I thought I heard Le Pen lost. I thought I heard that Le Pen lost.
Yes.
I don't know. Yeah.
So, of course, any technology will be used for war and sex.
Yes. Yes.
Let's change the topic. Let's change the topic to sex.
Actually, that's a very important thing. I mean, Joshua already mentioned this, but neural Darwinism is what I use. And neural Darwinism is basically reinforcement learning plus sex. So there.
I have to dig just a little deeper. The algorithms, are they more like mushrooms than diploids?
Funny you should ask that. They look like mushrooms once upon a time. I have a picture somewhere, but that was a bug in the system. We had over this project has been going for 21 years now, since 2001, and we have 23 versions of the system, and only version 21 and 23 worked. It took me 16.5 years to get to a system that could get to 0% errors. And now we're working on stuff on the levels about that. Yes. But
I remember your demo from 4 years ago. Thank you for sharing.
Yep. Yeah, this is the third event that I showed this learner to. I showed it at an AI meetup, and I showed it at the thing at the place.
All right, I'm going to ask one last question. What are you going to do next? What are you going to do next?
I'm working. I can't talk about it too much in public, but if you talk to me on the phone, I'll explain what's going on. But in general, there is a layer that I have to figure out, and I am 4 years into figuring it out. And we have very interesting results, but basically we are gone to the point where this very fast learning that we're doing is not going to scale to the next step, and we need a much larger machine. So an $80,000 machine from Supermicro would be what we need next. And that would have, like I said, 3 terabytes of RAM and 220 cores or something like that. That would be yummy. By the way, my system is completely thread safe, which means that I can have 200 pairs of eyes reading a book each, so to speak. I mean, 200 input senses of text, learning into the same brain at the same time, not a problem. So I can read 200 times faster if I just open more books at the same time.
Mario, can't you just get a grant and get access to a supercomputer and get all the computing capacity that you want?
I don't have the money. I mean, I don't even know how to get a grant. Nobody understands my tech. I've been turned down by so many, it's not funny. So yeah.
Really?
And by the way, I'm not good at grant writing. I'm not good at grant writing either.
You've gone through the SBIR process?
I tried. I talked to DARPA. I talked to the Air Force. I talked to Google. I talked to Apple. I talked to, yeah. Some of these were very brief encounters because they didn't want to even talk to me. So yeah. But I basically tried to push it for a decade or so, and nobody understands it enough to buy it. But I mean, part of the problem was that first part of the decade, the system didn't even work. I mean, everything I did before 2017, last time I asked a VC for money was 2 months before it started working. That's not really what you want to do. And I was too tired at that point to go back and ask for more.
In your system,
that sounds like you should. Sorry.
Oh no, go ahead, please.
That sounds like you should take a break so you're no longer tired, and then reap the benefits of your algorithm when you are relaxed again and optimistic again. I know how hard it can be to deal with rejection and setbacks and so on, and eventually we'll settle back into the healthy equilibrium. I hope that this all works out in the best possible way.
Actually, it turns out that I am actually economically stable at this point. I just don't have the ability to pull in $80,000. I mean, I'm working for a company that is going to use my technology. I'm writing their end of the API, and I get to keep all the intellectual property myself for the server end of stuff and for the learner. So that's a very sweet deal. So I have a little bit of an income, and I can continue doing this for years. And I've done it for, like I said, since 2017. I've done a lot of work on the next thing, next secret layer, and that has all been paid for by this company.
Monica, have you made videos that you put on YouTube and so on? And
yes, I have made lots of videos. I mean, you should. The easiest way for anybody to find my reference is to go to Facebook and look at my homepage. I also have look at my left column on my profile, but I also have so I have videos on Vimeo. If you go to Vimeo and look for my name, you can find a playlist of videos that I made, and there's I think 6 of mine and 1 by Peter Norvig or something like that. And then I have a website. The main site that discusses these things is artificial-understanding.com. It's a Medium site, but I have a DNS name on it. And that basically tells the story of epistemology. It's a primer in epistemology for AI people, basically. Discusses what I just talked about. This goes a little bit further because that site was written 5 years ago, but it's all the same story. The reductionism, holism has been the theme of my talk since 2005, 2006, after Google.
Have you tried China? I mean, they got stacks of money.
Yeah, they do. And one of the things that this system is good at, or should be good at, I actually tested it only very many years ago, but it should be good at Chinese word segmentation, which is an important problem. It's worth millions of dollars per year. Basically because Chinese don't put spaces in, and you have to put the spaces in if you want to do anything with the language, such as index it in a search engine. And the majority of errors in Chinese search engines are still segmentation errors. So this could do that if there was money for it. Maybe there is, I don't know.
Have you thought?
I haven't tried. My Chinese, I tried it on 6 different languages. English, Swedish, Finnish, French, German, and Russian. And I did Chinese like 5 years ago.
No, I don't mean the language. I mean going to China or approaching Chinese people and asking them for money. There's lots of money in China, especially for AI. It's one of their government's target areas. One of the 25 areas.
Well, I am looking for collaborators of all kinds, and that implies people who understand these kinds of things. It also means that I'm looking to hire people that are basically, what is it called, deep stack cloud people and others otherwise like that. And because I've been doing deep stack forever and I'm tired of it. Full stack Java programming. So now, but I'm currently in at least 2 different processes to look for funding. I won't talk any more like that, but there's a couple of ways that I could fund this shortly, and it will be important for me to find people to work with at all levels, including CEO is open, more researcher positions are open, and cloud programmers positions will be open. So yeah.
Yeah, I was going to ask if you have thought of publishing some of these ideas of especially the models, well, like the methods in like some research journals or venues of any kinds. I mean, I know it can be hard if the ideas are like quite different from some, but like, I mean, you can try to find some, I mean, not necessarily the hardest to get venues, but some trade-off which at least can give some visibility, and also like some feedback from the community which can help in future interactions. I mean, yeah.
So I have a paper called exactly the red pill of machine learning that I'm trying to publish, and I'd like to find a magazine to publish it, but I'm not an academic. I'm not in academia. I haven't been in academia since whatever. And so what I write is typically slightly easier prose, and it's more like a blog post, if you will. If you read my artificial understanding website, that's the style I'm writing in. And the paper that I have is not scientific enough. It's not formatted right, etc., to even make it onto archival.org. I mean, it's
I see. I mean, it may be worth.
By the way, I would need the endorsements from 2 published authors or something like that before archive even will look at it.
Oh, I see. Well, so maybe that will be an interesting area of future collaboration if you find people who are in academia that are willing to collaborate, and maybe that could be.
Yeah, I actually have a couple of signatures already, so I might go this route, but I'd rather publish it on some other site. I mean, and I have about 5 websites, and they all died in a stupid IP re-enumeration event, and I haven't had the time to set them up again. And so now I'm planning to start over with a new corporate website that contains all of this information and all of my blogs and lots of stuff from elsewhere. And I'm contemplating writing a book too. So there we are.
Okay.
It seems to me like, especially if you're saying that, you know, you provide understanding as a service, that, you know, your API or whatever could be used for a monthly subscription fee or something.
Yes,
and in that regard, I'm also wondering, like right now I understand, okay, your model is like much faster at learning and requires much fewer resources, so you can just upload the text, and then the output is just as reliable as any of these, you know, bigger, more expensive systems. How does it change now the more data you feed into your system? Is there any any difference that you can describe? Because I mean, you know, honestly speaking, at this point, we've used the bad models, but the output is the same. So where's the difference now? Of course, I understand. Again, you have a system that learns much faster and everything. But if I compare to GPT-3 or DeepMind or whatever else, I don't know half of those. But where's the difference now that they already have their understanding and their network populated and everything's developed?
Right. Well, so let's start with the fact that tens of thousands of deep learning researchers have been working on this stuff since 2006 when Hinton and friends came up with it, and since 2012 when it became public. And I'm the only one, me and my co-researcher Roger, we are the only ones who are working on my stuff. So we are not I mean, the injection of money would mean that we could hire more staff and more researchers, and we could take this to the next level very quickly. And also we need this bigger machine. So that's been the current plan for a while now. One thing that's interesting is that you can try to sell the service as I do, as understanding as a service. But there's also the temptation to start something else, such as a social medium, where this is the core technology. And one of my funding efforts is actually going in this direction. So I might end up working in a social media company doing this research, and everybody else is doing the system. That's my, hopefully, that would be a good way to get to the next stage.
It wouldn't be adult friend finder, would it?
No, it would be something you would very likely like. We can talk about it offline. If anybody's interested in working in the social medium using this as using my technology as a base, tell me and we'll make it happen. We'll see if you fit. We've done language generation experiments. We haven't, it turns out that the reason I got into this model in the first place, because I stumbled upon the secret of how to generate language in a book. And so I thought about it for a year, and then I started writing code. And the language generation is fallen by the wayside at the moment, but every now and then we dust it off and run it again, and it still runs pretty poorly, but give us an $80,000 machine and we can make it better. In general, all of the machine learning systems, I mean, they get better with bigger corpora because they fill in more of the corner cases. If you have never, I mean, if I'm writing, this is one reason we have multiple dictionaries. I mean, the system I'm building is going to basically have it's going to be a set of understanding machines, but for each of the service calls to the understanding machine, you have to specify what's going to be your competence, what competence are you going to use. And the competence we looked at now is basically called EN basic. It's English/basic. It's like a directory path, if you will. And the first two letters are always the country code. So we have EN/basic, and we will in the future have things like EN/medical, EN/legal, EN/social media, JP as in Japanese /social media, Finnish/medical, etc. So we can create hundreds of languages, cross it by dozens of domains in each language, and we can sell razor blades until the cows come home. And also, one of the tricks I'm going to use is I'm going to have basically I'm going to have an online service where people can submit the corpus, and it automatically learns the corpus and puts it out there for others to use, and the person who submitted the corpus gets a fractional kickback. So we can use basically volunteers all over the world to do things like give us a decent corpus for Urdu, and we don't even have to test it. They just create it, and if people like it, they will get a kickback and we'll get the money. So yeah, the core, the code size for the runtime in the cloud, the one that I have in the cloud at the moment, the inner loop is 91 lines of Java, 91. The whole code is mostly loading the core, loading the competence that comes from the learner and some logging and some accounting features. But 91 lines and you can understand English if you are given the right neural network structure. And I can warn you that you will not understand the code on the second or third read through. It's very compact.
Monica, I have a challenging question.
Shoot.
So language understanding, that veers off into satire, irony, and of course, puns.
Yeah, one of my early projects, which I never finished, was basically write a version that will read Jane Austen and underline every joke in green. She's pretty dense with jokes, I have to say.
It's been over 40 years since I read Austen.
Yeah. The rules were too large for her to move in with ease. Anyway.
So I'm a bit curious about this machine you want to buy. You're going to get it from
Supermicro.
You're going to get it from Supermicro. Okay. What are you building?
It's a 2-rack unit with 3 terabytes of RAM in 128 gig chips and 2 AMD CPUs with 110 or so cores each. That was the last time I looked. They make new machines so quickly that I may have to ask for more money because now something better is available. At the top end of this range, I can get a 12 terabyte machine at about $2 million. But then I have to do what is it called? Hyperchannel programming. I have to what is it called? There's this protocol that they use, which is much faster than Ethernet in the hundreds of gigabits range, whatever. I forget what it's called. It has a stupid name like hyperchannel, but it's not that. Mellanox, the Mellanox web. That's what we'd have to put in. So yeah, it's been a fun 21 years. I was doing reductionist AI most of my life, well, large fraction of my career. And then in 1998, I had a religious conversion to holism, if you will. That's what it took. And some people, when they are confronted with this, it's like a red pill. They may be unhappy about having learned this. And it really upsets one's worldview a lot if you accept basically that holistic methods can do things that reductionist scientific methods cannot. And we are in the middle of that right now with deep learning. I'm walking to the side because my screen of everybody else is on the side of my desk here. So sorry if I'm disappearing from the picture every now and then.
Monica, I go almost all the way with you. There's one thing that is left out in my understanding of the general problem, and that's having a body.
Favorite topic. So, embodiment. Let me kill off embodiment right away. Basically, people who go for the embodiment architecture or embodiment, argument, that they say basically we need to have an embody so that we can interact with the world, etc. We have to have a robot. That's a very human-centric point of view. And we know, for instance, that we can learn about the world from just reading text. We don't need to taste and feel an orange to know what an orange is. We see orange enough times in the text, we can make all kinds of conclusions about what an orange does. We can learn about nuclear power plants. Nobody's ever seen a proton, but we can build nuclear power plants based on nothing except stuff that we read in books. Okay, so the embodiment is not necessary. The reason we got into the embodiment argument in the first place is because people noticed that they couldn't do epistemic reduction, but they picked the wrong answer. You need to actually face the epistemic reduction problem directly, so you can look at the complex world and deduce what's salient and what is important in it, and discard the rest, like I explained in the photograph example. You have to do that, and whether you have a body or not, if you can do that, the body doesn't matter. So that's my opinion about embodiment and enactment. I think that will ruffle some feathers.
You and I have been having this conversation for years, and we respectfully disagree.
Yes, that's fine. There's many people who like embodiment. I just figured out that I didn't need that.
I think it's what produces the base upon which the other stuff grows, emerges.
Human-centric, human-centric. I write under text under language understanding machines. I don't have to move around. I mean, let's consider this. There's people who basically say that you heard of the Moravec/Woz test about an AI should be able to walk into any house in any city in the US and make a cup of coffee, right? That's the Moravec-Woz test for AI. And that is basically says, hey,
test, right?
Wozniak, yeah, Wozniak and Moravec. Moravec said it first, but Wozniak picked it up.
Okay.
So that's, at least that's how I remember it. Don't quote me on that. But the point is that means that AI is basically a lost cause for everybody except the roboticists, and I don't like that answer. I say that anybody who can do autonomous epistemic reduction is an understanding machine. If you can look at the complex world and decide what's important, pick out the highest level important concepts that are important to you at this moment. If you can do that, you are basically an AI.
I agree with you generally. I would point out that this test is actually the AI equivalent of Heinlein's competent man.
Mm-hmm. I have to think about that, but yeah. It was a while since I read that.
I would also say that most people walking into my kitchen would not be able to make coffee.
Yeah. I use an AeroPress. They're great, but not everybody knows how to use them.
Well, people get confused by dials that have readings and bars.
Right.
I mean, that's where what Monica mentioned about, continuous learning and self-improvement is important. Of course, at birth, everybody, doesn't know something. So that's where the systems need to improve over time.
Exactly. Yeah. I mean, I'm starting out with an empty machine, and it will learn whatever language I feed into it. Finnish works just fine.
Monica, has it ever occurred to you that your work amounts to a disproof of Chomsky?
Absolutely.
Cool.
My point on that, my soundbite on Chomsky is that any brain that's powerful enough to analyze our visual field can learn language as a minor side task. Okay. The visual field is so much work.
Chomsky might be using the word understanding in a different way than you are, Monica.
Well, Chomsky talks about this. Chomsky talks about this inherent language model, which is what I'm objecting to. And I'm saying, you don't need those. That's overkill. Any brain that's good enough for vision will handle, and music, for instance, will handle language just fine. You don't need to postulate a separate language sense in the brain for any reason. my opinion.
Fly brains,
Excuse me?
50,000 odd neurons, fly brain.
Yeah. It takes that you can do amazing things with very few neurons. Like I said, I can run language understanding and get 100% right on the Raspberry Pi. With 60 with some, I forget, 60 million neurons, no, 40 million neurons, something like that. It's in the tens of millions. And I've done it a few times, different times. So it's it might have, all of those numbers might be correct.
Have you thought about training your models on other sequential data sets other than linguistic? There are all kinds of things.
Yeah. Could you name one? Yeah, DNA is definitely in the possibility. MIDI music is another one. That would be reasonably easy, and I have a piano right there, so yeah, it would work.